How's everybody doing out there? So now that we've figured out where our measure of center is, now it's time to move on and figure out what our measures of spread are, or how wide our data is, or how close together it is. So if you remember from our box plot, we kind of could see the overall width of our set of data by having the min and the max there and stuff like that. And so we're actually going to use that as kind of one of our measures of spread. That's going to be what's called our range, which is the easiest measure of spread to find. Not always the most useful because it's really just going to give you a number that kind of lets you know, like this is how many numbers there are between the highest and lowest score or whatever it is we're talking about. So the one that's going to be the most useful for us is going to be the standard deviation. That's the one that we're going to use most often. And it's also the one that's a little bit more complicated, especially if you're doing by hand, to calculate. So luckily we'll have a nice little calculator trick that we can use that's going to make life easier. But I am going to kind of demonstrate how you can do this using the calculator, but in a by hand kind of way. All right, so let's first talk about the range since it's the easiest. So the range again is just basically finding the what the difference is between the upper and the lower value is for our given set of data. And that's exactly what our formula looks like. We're going to take the largest data value minus the smallest data value, and that's going to give us the range. So it's really telling us how many numbers are there between the top number and the bottom number. And so again, sometimes useful, but not nearly as useful or as powerful as the standard deviation is going to be for us. All right, so if we look at our standard deviation, so again, we've got two formulas just like we did for our mean. So the one with the S beside it is going to be our sample standard deviation. So I'm just using SD to abbreviate standard deviation. And so again, using our terminology from before, this is going to be our statistic because it's related to the sample. And as you can see, there's a lot of stuff going on in there. We've got some square roots. We've got that big sigma, which is our sum symbol. We're doing some subtracting. We're squaring some stuff. We're dividing. So pretty complicated. This is not necessarily an easy thing to do by hand, trust me. All right. Our second equation is going to be for our population standard deviation. And so in this case, that little Greek symbol here is actually lowercase sigma. And so this is going to be our sigma represents our population standard deviation. And so again, this is going to be our parameter for that set of data. And so again, notice pretty much the same formula. So now we have swapped out. So notice in this case our x bar is our sample mean. And then here we've changed it out for our population mean, which again makes sense because the bottom equation is working with our parameter. So we want to make sure our parameters always stay together. We want to make sure our statistics always stay together. So just so I can kind of summarize like what's going on with this formula, like if you were to think about this like in terms of order of operations, what you would do, the x represents all of our data values. The x bar is of course our sample mean. And so what we're doing with this equation is taking each one of the individual data values and subtracting them from the sample mean. So if you look at the example below, I'm not going to have you do this, but that's actually what we're doing in this case. Like, so this is how you would have to do this by hand. You'd have to fill out this big chart and all that kind of stuff. So I'm going to show you a little quicker way and then an even faster way after that. So after we find all these like differences, we're going to square each one of them. So that's what the square of the deviations are. And then we're going to add all those deviations together, divide them by n minus 1, which is 1 less than the total number of elements in the set, then square root that whole thing, and that finally gives us our standard deviation. So again, fairly complicated, can be a little bit tricky and stuff like that to do. So what I'm going to do is I'm going to show you a little trick that we're actually going to use in other parts of the semester. So that's why I want to go ahead and kind of get you thinking about it right now. So what we're going to do is we're going to kind of use our calculator in a way to help us do this, but it is still a kind of by hand way of calculating it. So where that x is in our list or in our equation, we're going to actually put in all that data into list 1, and then we're going to write kind of a big formula that'll do this for us. So let me kind of write out what this is going to look like in terms of what's happening here. So it's going to look like the square root of the sum of list 1 minus our sample mean squared, all divided by our n minus 1. So again, this is kind of ugly. If you don't quite get this, don't worry about it too much, because I'm not going to have you calculate it this way, but I did want to kind of demonstrate it on the calculator just so you could see kind of what's going on. And then eventually we are going to use this for some other things, but hopefully we'll be more familiar with it. So if this gets a little tricky, don't worry about it. You can skip this and then focus on how to calculate it using our 1-var stats, which is much easier. All right, so the first thing we need to be able to do to use this formula is we first have to figure out what the mean is. So what we need to do is take all these numbers from example 1 and put them in list 1. So these are all going in list 1. And I've already done that, fortunately. So if we go to the calculator, go to stat edit, in list 1. So here's all those data elements that we had there. So let's first find our mean by doing the 1-var stats. And so again, this is list 1. And so our sample mean is, of course, the 10.4 that we have there. So let's copy it over. So our x bar is 10.4. And so I have all this stuff in list 1 already. And so if I notice there's 10 fifth graders, so my n is 10. So when I'm looking at doing this bottom, I can think of this as basically 9 in this case. So to kind of write out what this formula is going to look like and what we're going to type into the calculator, we're going to get the square root of the sum of list 1 minus our mean 10.4 squared, all divided by our n minus 1, which is 9. All right, so let me show you how we can type this into the calculator. So it gets a little ugly, so again, you may have to pause it and stuff like that. But again, don't get too bogged down if you can't do this necessarily, because I'm going to show you an easier way in a second. But all right, so let's go to the calculator. So first thing we want to do is do our square root. So we're just going to do second x squared button, gives us our square root. Now to find our sum command, what we actually have to do is go into kind of where the second stat is. That's going to be our list option. So if we hit second stat and go into list mode, if we go over to math, on mine it's number 5, so we can see sum is one of our options. And so what I want to do is I want to put parentheses, another parentheses to represent that subtraction that we're going to do. So in this case we're doing list 1 minus our mean, which was 10.4. And then we want to square that. And now we want our second parenthesis to close off our sum. And then we want to divide that by our n minus 1, which in this case was 9. And so assuming everything's typed in correctly, if we hit enter, we shouldn't get an error, so knock on wood. Good. So we got 0.6992 appears to be our standard deviation for this guy. So let me write that down. So 0.6992. So our standard deviation. And so again, this is sample data that we're working with, so I want to use lowercase s instead of sigma, which would be population data. So our s is 0.6992. All right, so again, if that's a little confusing, Just, don't worry about it too much. So let's go back to our 1-var stats real quick and take a look at what's there. So if we go back to our 1-var stats that we had before, so if we do stats, calc, 1-var stats, list 1. So if we notice on our left-hand side, or towards the top, so there's this letter SX and sigma X. So lo and behold, our standard deviation is actually built into our 1-var stats, along with our min, our Q1, our median, our Q3, our max, plus our sample mean that we've been talking about. And so if we look at our SX, notice 0.6992 is exactly the same thing we got when we calculated this by hand, so sort of by hand. And then our sigma sub x, notice, is slightly different, but then again, if you look back at the formula, the original population standard deviation divides by the whole number n as opposed to n minus 1. So that's why these are slightly different. But again, for us, we're always 95% of the time we're going to be interested in calculating the sample standard deviation, so we want to use that S of x that's on there. So in this case, that 0.6992 is going to be the quicker, more appropriate way. So this is how I want you to calculate the standard deviation using the 1-var stats. All right, so let me pop back over here real quick now that we've done that. So again, in our green box, we've got our SX or sigma X. How do I know which one to use? So again, it's all going to depend on whether we're working with sample data or the statistics, or population data or the parameter. But again, usually what we're going to be interested in is going to be the SX for these guys. So it's pretty rare that we're going to know the whole entire population data where we'd be able to use the sigma sub x. But all right, so perfect. So next thing we want to talk about is we want to introduce this idea of z-scores, which is basically a way of measuring how many standard deviations away we are from the center of a set of data. So first thing we want to do is we want to take the set of data we have, find the mean and the standard deviation, and then I'm going to use that as a way to help us find some of these z-scores. So again, using our 1-var stats to calculate both our mean and our standard deviation, we'd want to type in all these numbers into our list. And so I've already done that for us, luckily. So if we go to stat edit, and list 2, I have all these ages of baseball players already in there. So we're ready to go. So we can just use our 1-var stats. So we're going to hit stat, calc, 1-var stats. But in this case, all my data is in list 2. So I want to make sure I denote list 2 for that. Hit enter. And so I can see that my sample mean is the x bar, so it's 28.85. And my S sub x, because again we're dealing with sample data, is going to be 5.37. So I'm just going to round this to 2 decimal places. So I've got 28.85, 28.85, and 5.37. So that's nice and quick. That's going to be our x bar and our S. So again, using 1-var stats makes life much, much easier to find that standard deviation. All right, so now what we want to do is we want to actually kind of lay out what the one standard deviation below the mean would actually represent. So I'm actually going to do more than just one. I'm going to do 1 below, 1 above, then I'm going to go 2 below, 2 above, then 3 below, and then 3 above. And then this is going to relate back to our z-scores. And this is something that you'll also do kind of in the homework as well. So when we're laying this out, what I like to do is think of this laid out as kind of a number line. And at the center of our number line, of course, is going to be our mean. So we've got our mean is right in the middle at 28.85. And so if I want to go 1 standard deviation above the mean, so from here to here, is going to be 1 standard deviation above the mean, so 1s. So I just want to take that 28.5 and add 5.37 to it. So if I do 28.85 plus 5.37, so that gives me 34.22. And so that's going to be 1 standard deviation above the mean. And so now I want to go, say, 2 standard deviations above the mean. So in this case, going from here to here is going to be 2 standard deviations above the mean. And so what I want to do is just add 5.37 to that 34.22. 5.37. So that takes us up to 39.59. And then finally, I'm going to go the whole way up to 3 standard deviations away from the mean. And so again, same thing. I'm going to add 5.37 to that second standard deviation. So I'm just going to do plus 5.37. And so that gives me 44.96. And it turns out, we'll talk about in a little bit, like that we really don't have to go any further than 3 standard deviations away from the mean to pretty much capture all the data that's ever going to occur in a set of data. All right, so now if we want to go standard deviations below the mean, instead of adding, we're just going to subtract that 5.37 from the 28.5. So minus 5.37. So this gives me 23.48. And so this is minus 1 standard deviation away. And so if I want to go minus 2 standard deviations away, I'm going to subtract 5.37 from that 23.48 to get 18.11. And then finally, one more time, if I want to go minus 3 standard deviations away, I'm going to minus 5.37 from that 18.11, and finally get 12.74. So what this idea is eventually there's a nice rule, and we're going to talk about it at the very end of the section, so I don't want to give it away. But basically, when you lay out your data in this fashion, there's a certain percentage of data elements that we're going to expect to have that lives in between each of these different numbers. And that's one of the reasons that it makes this using standard deviation compared to range such a powerful measure of our spread of data. And so again, pretty much almost all of our data is going to live somewhere between this 12.74 and the 44.96, and we can see from above that that's actually definitely true, because we don't have any scores below 12.74, and we don't have any ages above 44.96 either. But all right, so just hang on to that for a little bit. Just make sure you kind of remember, if you take the mean, keep adding the standard deviation, that can build our upper part, subtract the standard deviation to build our lower part. All right, so finally, let's talk about our z-scores. So our z-scores are actually the scores that we have, that we've calculated, are in fact z-scores themselves. These just happen to be very nice z-scores. So in this case, this 34.22 is the number that we get if we have a z-score of exactly 1, because it's exactly 1 standard deviation away from the mean. The 39.59 would be a z-score of 2, because again, it's exactly 2 standard deviations away from the mean. And finally, our 44.96 would be considered a z-score of 3, because again, it's 3 standard deviations away from the mean. The 28.85, the mean itself, this would actually be considered a z-score of 0, because it's no standard deviations away from the mean, because it is in fact the mean. And then all these values to the left are going to still be nice whole numbers, but since they're to the left of the mean, they're all going to be negative. So that 23.48 would relate to a z-score of -1. 18.11 is going to relate to a z-score of -2. And then finally, 12.74 is going to relate to a z-score of -3. Now, unfortunately, the likelihood that we land exactly on one of these perfect z=1, z=2, z=3 is pretty slim to none. So what we want to do is we want to be able to actually calculate the z-score exactly for a given value, even if it doesn't happen to be a nice whole number or anything like that. And so that's what we want to talk about in this next little section here. And so our z-score, again, is just a number that represents how many standard deviation away it is from the mean. And to calculate our formula, or to calculate our z-score, we're going to use the following formula, where in this case our x represents the number that we're trying to find the z-score of. So it represents the data value of the z-score we're interested in. Our x bar is, of course, our sample mean. And our s is, of course, our sample standard deviation. So we're going to calculate this little fraction. That's going to give us a z-score, and that'll kind of tell us, like in a number line perspective, how far away we are from the mean, whether we're to the right or the left or any of those things. All right, so let's take a look at so we're still using the example from above. So in the baseball team age set above, we want to find the z-scores that correspond to a person that's 26 years old and a person that's 32 years old. So again, before we can do anything, we need to make sure we remember what the sample mean and the standard deviation is. So if you've forgotten, let's just go back up and check here. So we've got 28.85 for our sample mean and 5.37 for our standard deviation. And so the 26 and the 32, these are the individual x's that are in our set. All right, so let's plug this into the equation just so we can see what it looks like. So in this case, our x goes first, so we're going to get 26 minus 28.85, and then we want to divide that by our standard deviation of 5.37. It's supposed to be a 5. And so I put parentheses around this just in case if you're typing this in the calculator, if you do it in one step, you want to make sure you put parentheses around the top and then divide by that 5.37. Or you could do it as two separate steps, do 26 minus 28.85, hit enter, and then divide by 5.37, in which case you don't technically need the parentheses. But if you use the parentheses, we'd want to put them in at the same time. 7, and so I got negative 0.53 for my z-score. And so since I've got kind of that little number line up above that we drew, let's go up and see on our number line, does that negative 0.53 kind of make sense? So again, the score that we're interested in is the age 26, and notice negative 0.53 seems pretty reasonable for this guy because it's definitely less than 0, but it's bigger than our -1, so that z-score looks to check out pretty well. All right, so let's take a look at our x equals 32, and so again we're going to do the same thing. So z equals 32 minus our mean divided by our standard deviation of 5.37. So again, type this in the calculator. 32 minus 28.85, oops, divided by 5.37. And so with this one we got 0.59, it looks like. And with z-scores, the typical rounding for z-scores are always 2 decimal places. So for z-scores, always round to 2 decimal places. All right, So again, let's kind of go up to where we drew our little number line and just verify that that 0.59 seems reasonable. So our 32 is again going to be somewhere here in the middle, and so z equaling 0.59 seems pretty reasonable of a z-score for that. So that looks good. Perfect. All right, so if you have any questions or anything about that, definitely let me know. If you're having trouble getting the same answers I'm getting or anything like that, typing them in the calculator, let me know so we can make sure we're not making any kind of mistakes with that. All right, so finally, this is where z-scores can come in pretty handy, because z-scores allow us to take two sets of data that are similar but different and actually compare them. And so what do I mean by similar but different? So this example 4 is a perfect example. So if you notice, some colleges, and you may have taken these at some point in time yourself, some colleges take SAT and ACT scores as a way of letting people know whether they get accepted to the college or not. But if you've taken these tests before, you know that their scores are drastically different. The SAT scores are in the thousands, hundreds and thousands. ACT scores, I think, are less than like 24. And so they both are accomplishing the same goal. They're both trying to decide whether you're getting into college or not. But we really can't compare the two scores because the hundreds are always going to look significantly bigger. But the nice thing is, if we take and convert both of these sets of data into z-scores, now the z-scores, regardless of what the original data looks like, are going to be something that you can actually compare each one of them to. So again, that's what's kind of the cool thing about them. So in this case, we're trying to decide, should we put forward our SAT score or our ACT score? Which one is the stronger score? Because we want to make sure we get into the college of our choice and things like that. So we want to put the best score forward to give us the best chance of doing that. So when we're thinking about a problem like this, we're trying to figure out which score is going to give us the biggest z-score possible. So let's go ahead and calculate the z-score for both the SAT and the ACT, and then decide from there which score we should put forward. So I'm going to do the SAT on this side, the ACT on that side. And so notice our mean is given, our standard deviation is given for both of these. And then our 550 is going to be our x, and our 24 is also going to be our x for our ACT. So using our formula, x bar all divided by s. So we're going to get z equals 550 minus our mean of 500. All divided by our standard deviation of 100. So when we type this in the calculator, we're going to get, oops, so it looks like we get a z-score of 0.5 for our SAT score. So not bad, so it's definitely above the average, so it's not way out in the 3 range. So it's not necessarily one of the highest SAT scores, but it's definitely bigger than average, which is good. And so our ACT, we're going to get our z equals 24 minus 18, all divided by 6. And so if we throw this into the calculator, I think we get, 6 over 6 equals just 1 in that case. So in this case, since our z equals 1, compared to our z equals 0.5, our ACT is a stronger score compared to other students. So our ACT score is a stronger score to other students. So if we only could submit one score, our ACT is going to give us a better chance at admission to colleges than our SAT would in that case. All right, so good job, everybody. So this actually, I've got one little section left here, almost forgot about. And so this kind of piggybacks on what I was talking about before on why the standard deviation is so popular compared to the range in terms of talking about our measures of spread. And so, and we're not going to work with this at the moment. We are going to work with this at a later date. But there's this nice little rule called the empirical rule, or it's sometimes called the 68, 95, 99.7 rule, which gives us a way to break down a normal curve in terms of its standard deviations and allows us to talk about what percentage of values actually live between certain sets of data and stuff like that. So if we look at our rules, so here's our little, one standard deviation away from the mean, two standard deviations away from the mean, three standard deviations away from the mean. So these are what we had calculated on our own in the previous example. And so if we notice in blue, so 68% of the data lives between one standard deviation below and one standard deviation above the mean. So if you're within that range, we know that 68% of all the data is going to live there. Now, if we go out to two standard deviations, so this is going to be the yellow and the blue combined, so 95% of all the data is going to live in between those two ranges of values. And then finally, lastly, if we go out three standard deviations, then in this case 99.7 are almost all the data other than possibly outliers. So that's really the only thing that's kind of missing from this set, is they're given that possibility there are some outliers in there. So within three standard deviations, we're going to expect all the possible data elements to live within that chart. So that's why I'd mentioned above, there's no reason to go out four standard deviations or five or six or anything like that, because of this nice empirical rule, we know that all of our data should live somewhere between three standard deviations above and three standard deviations below of our mean. And so this rule is only true if we've got a nice normal curve. And so that's where that little bell-shaped curve is. And so again, I'm kind of getting ahead of ourselves. We're going to talk about this stuff later, so don't get too bogged down in it at the moment. Now, if our curve isn't normal, then we can actually still talk about the standard deviations in terms of the percentages and things like that using our Chebyshev's rule. And so in this case, this only applies to non-normal curves. So these would be ones that aren't symmetric. So it might look something like this maybe, for example. And so now this one, notice we don't talk about one standard deviation. So we have to start off with two standard deviations. But it's saying that within two standard deviations of the mean, 75% of all the data is going to live there, which is definitely not as strong as our 95% from above. But again, like these shapes are a little strange anyway, so we wouldn't expect to have just as nice of a percentage. And then finally, if we go out three standard deviations, so we can get up to 89%. So again, a far cry from our 99.7 that we had above with a nice normal curve, but at least it still gives us a way to actually estimate where the majority of the people live and be able to talk a little bit about it. All right, perfect. So I've got a bunch of practice ones for you guys to work on. So finally, this is the last day of using this set of data. So I'm sure you're tired of it by now, but luckily we typed it in once and hopefully we're done. So if you have any questions or anything, just let me know. Send me a message through the chat. And this officially finishes us up for chapter 12. So good luck, everybody. Let me know if you have any questions.